Today we're going to be looking at solving trig equations. And whenever we do this, we want to keep two things in mind. One being the unit circle up here, and the other being our table of exact values. Now I can imagine, say, something like the angle of 30 degrees, or pi on 6. We can imagine that on the unit circle. Now 30 degrees literally would be this straight line here, and it would represent a coordinate. Now, whenever we say that 30 degrees, we're imagining in here is pi on 6. And if I look at the coordinate, well, the coordinate here is an x and a y, the x being the cosine of pi on 6, and the y value being the sine, or the height, of pi on 6. We know this really because the unit circle has a hypotenuse length of 1. And so if I imagine the a over h, well, I'm talking about this line down the bottom here, the x values divided by h divided by 1. We can do this, we've done this proof in class and you guys should know that, but if you don't, we can do a separate video on it, just let me know. Now the way that we want to, I suppose, conceive these equivalencies is imagine I had another point on this unit circle which is of exactly the same height. So if I imagine a corresponding y value which would occur here. Well, that same height, we might think, what angle is that? I know that it would be equivalent to being 30 degrees in the opposite direction. So I know that inside here, if I just get rid of this ruler, is pi on 6. And the height would be the same. So the overall angle would have to be pi minus pi on 6. In fact, that overall angle is 5 pi on 6. And that's where we get this nature of equivalence, that sine of pi minus theta is going to be the same as sine theta. Alternatively, we might have a look, and think, well, what's the equivalent cosine? Where are the x values the same? And if we were to draw an exactly straight line down from here, we're going to get this point there on the circle. And just as I adjust this, my apologies, you can see there that the overall angle, if we drew that in green, is going to go all the way around, and in fact will be 2 pi minus pi on 6. So there's always, this idea of repeating values. We can also imagine the nature of these repeating values by looking at a graph. So we can see there's a graph here, and if we look at that and we imagine, okay, where does sine theta equal 1/2? So where is sine theta equal to 1/2? Well, let's imagine a straight line for y, which we can see there, y equals 1/2. So if I just draw that over and make it a little bit clearer for you, there's going to be really 4 points of intersection over the course of 0 to 4 pi. In fact, there are 2 solutions for every period, or 2 solutions for every lot of 0 to 2 pi. So here are the first 2, and here are the second 2. But looking at the graph over one period, you can see that it will in fact repeat. So sine theta is one period, and then we're going to get a repeat of values. Now we can imagine this second thing here as being the exact same value of sine as pi minus theta. And likewise here, the green line is just the repeat over the period of 2 pi. So in general, all we really need to do whenever we're solving trig equations is look at the first quadrant, where all things are positive, and then think, what's the equivalence? Do I also need something that's in the second quadrant if it's sine, in the fourth quadrant if it's cos, or in the third quadrant if it's tan? So really important that at some stage we look to commit this table of exact values to memory. Now there are some few tricks for learning this as well, which I'm happy to link down in the description in a separate video. Okay, looking at our first example here, we really need to take note of the fact that we're given a domain. The domain in this case is that theta is an element of 0 to 4 pi. So thinking about this being 2 rotations of that circle, that unit circle, I can expect to see that over 0 to 4 pi, and I see here that the period is 2 pi, and there's 2 solutions for every period. So I can actually expect 4 solutions in this case. From my table of exact values, I know that if sine theta is equal to a half, theta is the inverse sine of a half, which looking at my table of exact values gives me the answer for pi on 6. Now that's only true in the first quadrant, so I need to think, well, where is it equivalent? Here's one answer, which we can tuck away for later, but the second answer is wherever the factor pi minus this theta. So let's imagine now I've got pi minus theta. Whoops, let's get out that pen. Well, in this case, the second answer would be pi minus pi on 6, which we know is equal to 5 pi on 6. So now I've got 2 answers. And over the period of 0 to 2 pi, these answers would be sufficient. However, we know that the domain is 0 to 4 pi, and we know that sine theta, so without any dilations from the y, without changing the period, the standard period is just going to be 2 pi. So I know I can add 2 pi to each of these basic answers, and I know I'm going to get the last 2. So if we started here by saying, well, we know theta, theta is equal to pi on 6 and 5 pi on 6. It's also going to be equal to pi on 6 plus 2 pi and 5 pi on 6 plus 2 pi. Now in this case I'll think of 2 pi as being 12 pi on 6. So 1 pi on 6 plus 12 pi on 6 is 13 pi on 6. 5 pi on 6 plus 12 pi on 6 is 17 pi on 6. And we know we still had our basic answers. The final thing here is that we may wish to answer in set notation. So I'm going to rub out this equal sign and rather state that theta is an element of this set of numbers. Now this second equation has something rather unusual in that it's not currently in the form of just cos theta equals something. But we know how to solve this. If we were to add 1 on root 2 to both sides of the equation, I can simply rewrite this as cos theta equals positive 1 on root 2. It's also worth noting the domain here of 0 to 2 pi. Now that's one period of cos theta, so I can expect there to be 2 solutions, one in the first quadrant and one in the fourth. Now that I've got this in the form of cos theta equals a or equals a constant, in this case 1 on root 2, I can use my table of exact values. So from my table, I know theta is the inverse cos of 1 on root 2. Now from my table I recognise that value as pi on 4, 45 degrees. So that's my base angle. I need to think which quadrant now is this going to be equivalent in? The fourth quadrant, which is to say that theta is also equal to 2 pi minus pi on 4. And that pi on 4, you know that we just got that from up here. So you can see where I'm getting these values from. Now 2 pi minus pi on 4, well that's like thinking 8 pi on 4 minus 1 pi on 4, that's going to be 7 pi on 4. And we can note in this instance that we really don't need to add 2 pi, because that would take us outside the domain of 0 to 2 pi. So all we need left to do is just answer that theta is an element of the set of numbers pi on 4 and 7 pi on 4. Now this question presents a couple of challenges for us. Now one of the challenges here that we haven't yet seen is that we now have cos of 2 theta. So if I imagine the period being 2 pi on n, so period is 2 pi on n. In this case it's going to be 2 pi on 2, which is pi. So that's our first challenge, is that we're going to have twice as many solutions. In other words, for every lot of pi, there'll be 2 solutions. The other thing that's quite interesting is the domain here is from negative pi to pi. So rather than just adding the period, or adding 2 pi to every set of solutions, we need to also subtract it, as we need some things in the negative field. So what I might do first of all is, rather than be a little bit upset about this 2 theta, let's just let x equal 2 theta. So that my equation now becomes cos x equals root 3 on 2. I can rearrange this as x is the inverse cos of root 3 on 2. And from my table of exact values, I know that x is going to be equal to pi on 6, or 30 degrees. Now the other answer, or the corresponding answer here, would be 2 pi minus pi on 6. So we know that we've got 2 pi minus pi on 6, our equivalent answer. Now we might think of 2 pi as being 12 pi on 6, and so we can recognise this as 11 pi on 6. Now remember here that x was actually 2 theta. And before I start thinking about all the possible ways I might do this, we're going to need to expand our field of answers. So not only will I take pi on 6 plus 2 pi and 11 pi on 6 plus 2 pi, I'm also going to take 11 pi on 6 and minus 2 pi. And I'll also take pi on 6 and minus 2 pi. So if I start with 11 pi on 6 minus pi on 6, I might need to rewrite my answers up here. So I know that 2 theta does have the answers pi on 6 and 11 pi on 6. But I suppose we might think of this as to the left of that. 11 pi on 6 minus 12 pi on 6 is going to be negative pi on 6. And pi on 6 take away 12 pi on 6 is negative 11 pi on 6. Now pi on 6 plus 12 pi on 6, or plus 2 pi's, are now going to the right. We know we've got 13 pi on 6. And the 11 pi on 6 plus 2 pi gives us 23 pi on 6. Now the last thing here is to solve for theta. So if I've got 2 theta, to get theta on its own, I'd multiply by half. And so on the right hand side, we also multiply by half. So I've got negative 11 pi on 12 now. Negative pi on 12, pi on 12, 11 pi on 12, the 13 pi on 12, and the 23 pi on 12. However, if I look at my domain of negative pi to pi, I know that negative 11 pi on 12 works. I know that negative pi on 12 works. Pi on 12 works. 11 pi on 12 works. But 13 pi on 12 is too big. And obviously 23 pi on 12 would also be too big. So my final set of answers, we might say that it's an element of negative 11 pi on 12, negative pi on 12, pi on 12, and 11 pi on 12. Now, here we have a very similar problem, only that we're talking about sine of 2 theta. So once again, I'm just going to take this 2 theta and let x equal 2 theta. And I need to recognise, here it's a nice simple one, that the domain is between 0 to 2 pi. However, the period in this case will be pi. And I can work that out by saying period is 2 pi on n, which in this case is 2. So I actually will have 4 solutions here. Remember, there are 2 solutions for every lot of pi, or for every period, and there are 2 periods in this domain. So if I rewrite this as sine of x equals 1 on root 2, you may recognise from your table of values that x must therefore be pi on 4. And the equivalent answer to this, remember we're in the second quadrant now, is pi minus pi on 4. So we're going to have an answer of 3 pi on 4. And we know that we have our base answer of pi on 4. Now from here, I'm going to add 2 pi. So pi on 4 plus 8 pi on 4 is 9 pi on 4. And here we're going to add 2 pi. So 3 pi on 4 plus 8 pi on 4 is 11 pi on 4. If I remember that x was actually equal to 2 theta, my last step is to divide by 2. So this pi on 4 becomes pi on 8. This 3 pi on 4 will be 3 pi on 8, 9 pi on 8, and 11 pi on 8. So if we're multiplying by half, we're just doubling the denominator there. And I may wish to write this as set notation. So I'll say theta is an element of this set of numbers. Now we can see from the previous question here that our domain is actually 0 to 2 pi, inclusive. And the only difference here is that we're after sine of 3 theta. So if I imagine that my period is 2 pi on 3, I know that in the course of 0 to 2 pi, there's actually going to be 3 solutions, or 3 periods. And if there's 2 solutions per period, there will obviously be 6 solutions between 0 to 2 pi. But we treat this exactly the same manner as we did before. Let's let x equal 3 theta. So now I have sine x is root 3 on 2, which from my table of values tells me that x must be pi on 3. And the corresponding angle, which would be pi minus pi on 3, so 3 pi on 3 minus 1 pi on 3, is 2 pi on 3. Now, because I'm expecting to find 6 solutions, I'm going to add a few lots here. So pi on 3 plus 6 pi on 3 is 7 pi on 3. 2 pi on 3 plus 6 pi on 3 is 8 pi on 3. 7 pi on 3 plus 6 pi on 3 is 13 pi on 3. And the 8 pi on 3 plus 6 pi on 3 is 14 pi on 3. Now if I remember here that my x was actually 3 theta, then I can make all these 3's a 9. And so I can rewrite my answer as theta is an element of pi on 9, 2 pi on 9, 7 pi on 9, 8 pi on 9, 13 pi on 9, and 14 pi on 9. Now if I were to keep going here, suppose I had have added 2 pi to the 13 pi on 3. I'll do this in a separate colour so that we know it's wrong. If I had have gone and added another 6 pi on 3 here, I would have had 19 pi on 3, which after we divided by 3 would have been 19 pi on 9, and that's bigger than 2 pi, so we would have ignored it anyways. We tend to get around this just by remembering that if I've got 2 pi on 3 as my period, there are 3 periods between the domain, 0 to 2 pi, I'm likely to have twice that many solutions, likely to end up with 6 solutions.